Good morning. So, in the earlier classes, we discussed about what is linear system, what is non-linear system, what is time variant system, time invariant system, linear time invariant system, and transfer function of linear time invariant system, and impulse response, etc. Okay, and also we have done some problems related to LTI systems. Okay, so LTI systems, what is LTI system? Linear time invariant system. So for this linear time invariant system with the given input and its impulse response, so we can find out the output. We can find out the output. Okay, like that we have solved two problems, two to three problems. Now and like this type of problems also, if the given system is linear, non-causal or non-invertible system, like that. Okay, next this problem was also solved. So here the impulse response is given, that is h of t equal to 4 into e power minus 4t into u of t. Find the graph and response of the system to x of t is equal to rectangular of 2 into t minus 1 by 4, or it is 2t minus 1 by 2, 2t minus 1 by 2. Okay, so it is it was also solved with three conditions, that is t is less than 0, t is greater than 0, and t equal to 0. Okay, already in the last class we discussed about the t is less than 0. At t is less than 0, we will get y of t value is 1 minus 0.0498 into e power minus 4t, and for t is greater than 0, we will get the value of y of t is equal to 0.318 into e power minus 4t for t is greater than 0, and for t equal to 0 we have to solve this one. So x of t minus k becomes here, by putting t equal to 0 at here, so that it will become x of minus k. So x of minus k is as shown in figure 5, that is it is the mirror image of x of k. X of minus k is nothing but mirror image of x of k. It is the reflection of x of k, which was shown like this. Okay, so it is it is in figure 5. For the values k equal to 0.25 to 0.75, the signal x of t minus k and h of k will both exist. Okay, then y of t equal to integral 0.25 to 0.75 1 into 4 into e power minus 4k dk, or by taking integration we will get the value of y of t is equal to 0.318 for 3 equal to 0. Now we will draw the three conditions. We'll draw the graph for three conditions, that is y of t equal to 1 minus 0.049 into e power minus 4t for t is less than 0, e power minus 1 minus e power minus 3 for t equal to 0, and e power minus 1 minus e power minus 3 whole into e power minus 4t for t is greater than 0. For these three conditions, we will draw the graph, that is the response y of t for all the cases is as shown in this figure 8. Okay, see here, here we see for t is less than 0, here it is varying, the graph is varying from 0.75 to 0, that is exponentially growing type. It is exponentially growing from minus 0.75 to 0. At t equal to 0, its value is 0.318. At t, for t is greater than 0, it is exponentially decaying from t equal to 0 to some value. Okay, so this is the graph for these three conditions: t is greater than 0, t is less than 0, and at t equal to 0. Okay, so this is the response of the function y of t. Okay, now we will see the next problem, that is find the transfer function of lattice network. Here the lattice network is given like this. We have to find out the transfer function. How to find out the transfer function? That is nothing but output by input. Here the output is v naught of t, here the input is vi of t. Here the transfer function, we have to find out the transfer function h of s. H of s is equal to v naught of s by vi of s. Okay, but it is given as V naught of t and Vi of t. So from this lattice network, we will mark the points. This point is A, this point is B, this is C, and this is D. Okay, so the potential across the points A and B is same as the potential across the points C and D. Similarly, the potential across the points A and D is same as the potential across the points B and C. Potential or voltage, whatever it is, both are same. Potential or it is also named as voltage. Okay, so simply you will rearrange this diagram so that we'll get some loops. Okay, so VA of t, this is 1 farad capacitor, and 1 henry, this is also 1 henry inductance value, this is 1 farad. So here one loop will be formed here, and here second loop will be formed here, and here the resistance 1 ohm is there. So here I1 and I2 be the loop currents. Now we will apply the Kirchhoff's voltage law to loop 1 and loop 2. First of all, for the first loop we will apply the Kirchhoff's voltage law, so that it will become VI of t is equal to, for this inductor, I into I 1 into d by dt of I1 of I1 plus this is the capacitor I1 minus I2. So 1 by 1 into integral I1 minus I2 into dt, plus for this inductor 1 into d by dt of I1. That is equation number 1. Now we will take the Laplace transform of equation number 1, so that we get VA of S. VA of S is equal to, for d by dt of I1, that is S into I1 of S, plus for this integration I1 of S minus I2 of S by S, plus S into I1 of S. So VA of S becomes taking I1 of S as common. So I1 of S into 2S plus 1 by S minus I2 of S by S. Okay, take this as equation number 2. In the same manner, we will apply the Kirchhoff's voltage law to loop 2. Okay, so that we'll get 0 is equal to 1 into I2 plus I2 minus I1 into 1 by 1 into integral I2 minus I1 into dt. Now again we will apply the Laplace transform for the above expression. Okay, then it will become 0 equal to I2 of S plus I1 of S by S plus I1 of I2 of S by S minus I1 of S by S. Okay, so I2 of S, take I2 of S as common, so I2 of S into 1 plus 1 by S minus I1 of S by S, so that I1 of S by S becomes I2 of S into 1 plus 1 by S, taking LCM as S, S plus 1 by S. Okay, from this expression I1 of S equal to I2 of S into S plus 1, SS gets cancelled. That is treated as equation number 4. Therefore, the output voltage V naught of t is given by V naught of t is across the resistor, 1 ohm resistor, that is I1 into 1, I2 into 1. So V naught of t is equal to 1 into I2. Again we are taking Laplace transform, apply Laplace transform for this one, so that V naught of S becomes I2 of S. So this is considered as equation number 5. So from the above expression 4, in equation number 4, replace I2 of S by V naught of S, or simply substituting equation number 5 in equation number 4, so that we will get I1 of S equal V naught of S into S plus 1. On substituting equations 5, equation number 5 and equation number 6, in equation number 2, we get VI of S is equal to V naught of S into S plus 1 into 2S plus 1 by S minus V naught of S by S. Okay, so VI of S, then it will become VI of S equal to V naught of S into S plus 1 into 2S square plus 1 by S minus 1 by S. So This is by multiplying this one, we will get 2s cube plus 2s square plus s plus 1 by s minus 1 by s. So 1 gets cancelled, plus 1 minus 1 gets cancelled, so that it will become 2s cube plus 2s square plus s by s, or taking s as common, s, that is s into 2s square plus 2s plus 1 by s. So ss gets cancelled, so that VA of s becomes V naught of s into 2s square plus 2s plus 1, or V naught of s by VA of s equal to 1 by 2s square plus 2s plus 1. So the transfer function or system function h of s is defined as V naught of s by VA of s for this lattice network, so that its value is 1 by 2s square plus 2s plus 1. Okay, so that is the transfer function of the lattice network, that is h of s is equal to v naught of s by va of s, that is equal to 1 by 2s square plus 2s plus 1. Now coming to the next problem, sketch the magnitude and phase characteristics of h of j omega. Already h of s is transfer function that is calculated in the above problem, that is h of s is equal to 1 by 2s square plus 2s plus 1. Now we have to sketch the magnitude and phase characteristics of h of j omega, but we have h of s, so replace s by j omega, so that it will become h of j omega. So h of s is 1 by 2s square plus 2s plus 1. So h of j omega is replace s by j omega, so that it will become 1 by 2 into j omega whole square plus 2 into j omega plus 1. J square is minus 1, so that it will become minus 2 omega square plus j into 2 omega plus 1. Or we can write these real terms on one side and imaginary term on another side, so that it will become 1 by 1 minus 2 omega square plus j into 2 omega. Now rationalizing the denominator. Now rationalizing the denominator, we will get 1 by 1 minus 2 omega square plus j2 omega into 1 minus 2 omega square minus j2 omega by 1 minus 2 omega square minus j2 omega, so that it will become 1 minus 2 omega square minus j2 omega by 1 minus 2 omega square whole square minus j square 4 omega square. J square value is minus 1, so minus into minus plus, so that it will become plus 4 omega square. So by expanding 1 minus 2 omega square whole square, that is in the form of a minus b whole square, so it is a square plus b square minus 2ab, so that minus 4 omega square and plus 4 omega square gets cancelled. That's cancelled, so that it will become 1 minus 2 omega square minus j2 omega by 1 plus 4 omega power 4. Okay, so h of j omega can be written as 1 minus 2 omega square by 1 plus 4 omega power 4 minus j2 omega by 1 plus 4 omega power 4. Okay, now we will calculate the magnitude calculation and phase angle calculation. Magnitude calculation can be calculated by taking mod h of j omega. Mod h of j omega is equal to square root of 1 minus 2 omega square plus 4 omega square by 1 plus 4 omega to the power 4 whole square. Okay, so that it will become 1 plus 4 omega power 4 whole power 1 by 2 by 1 plus 4 omega power 4, or mod h of j omega is equal to 1 by square root of 1 plus 4 omega power 4, that is the magnitude of the transfer function. Then again we are coming to calculate the phase calculation, angle of h of j omega, that is nothing but tan inverse imaginary part by real part. Here the imaginary part is minus 2 omega by 1 plus 4 omega power 4, and real part is 1 minus 2 omega square by 1 plus 4 omega power 4, so that it will become tan inverse minus 2 omega by 1 minus 2 omega square, or we can write this as angle h of j omega is equal to tan inverse 2 omega by 2 omega square minus 1. So by taking different values of omega, that is here we are taking both positive values as well as negative values. So we are taking omega from minus 3 to plus 3, minus 3, minus 2, minus 1, 0, 1, 2 and 3. Substitute these values in the above expression. Magnitude expression mod of h of j omega is equal to 1 plus square root of 4 omega power 4, so that we will get the corresponding values of mod of h of j omega are like this. So by taking the plot between mod of h of j omega and omega, we will get the response like this. So this is the magnitude plot or magnitude spectrum. And then coming to the phase spectra, phase phase plot. So here also we are taking different values of omega and substitute these values in phase angle, so that we will get different phase angles for different frequencies, right? So by simply taking the plot between angle of h of j omega and omega, we will get the plot like this. Okay, this is the phase spectra. The above one is the magnitude spectra. Okay, so this is the magnitude and phase spectra of h of j omega. Okay, right. Next, coming to the next problem, find the current I of t in a series RLC circuit. Find the current I of t in a series RLC circuit as shown in the figure. When a voltage of 100 volts is switched on across the terminals A and A dash at t equal to 0. Means that at t equal to 0 only, after t equal to 0 only, the current in the circuit is ready to allow the current through it. At t equal to t0 minus, it does not allow any current to the circuit. So given switch is closed at t equal to 0, that was given. Before t equal to 0, that is at t equal to 0 minus, at t equal to 0 minus, there is no flow of current to the circuit. Hence, the initial conditions of the circuit are 0. Initial conditions of the circuit are 0. After t equal to 0, the circuit is as shown like this. After t equal to 0, the circuit is shown like this. So 100 volts voltage is given. So 2 ohms resistor is there, 1 Henry inductor is there, 5 farad capacitor is there. With these values, a loop will be formed with I of the current flowing through this loop. Okay. Now we will apply the KVL to the above circuit. Kirchhoff's voltage law to the above circuit. So it will become V of t is equal to 2 into I of t plus 1 into d by dt of I of t plus 1 by 0.2 into integral I of t dt. That is treated as equation number 1. Now applying Laplace transform on both sides for the equation number 1, we get V of s is equal to 2 into I of s plus s into I of s minus I of 0. Here we are taking the initial conditions also, plus 1 by 5 into 1 by s into I of s plus 5 into V naught of V of 0. Okay, V of 0 by s, right? So here, as initial condition, as we already know that the initial conditions of the circuit are 0, so that I of 0 is equal to V of 0 is equal to 0. Then equation number 2 becomes V of s equal to 2 into I of s plus s into I of s plus 1 by 0.2 s into I of s. Okay. So from that expression, V of s by I of s is equal to 2 plus s plus 1 by 0.2 s, or I of s by v of s is equal to 1 by 2 plus s plus 1 by 0.2 s. From this diagram, input side is given as voltage v of s, and output side is uh, we are going to calculate the current I1 of the will flows through the capacitor with a 0.2 farad. Okay, so then output current by input voltage is nothing but the transfer function here, that is I of s by v of s is equal to h of s, where h of s is equal to I of s by v of s is the transfer function of the circuit, or h of s is equal to 1 by 2 plus s plus 5 by s, or it is s by 2s plus s square plus s, or we can write this as s square plus 2s plus 5, that is considered as equation number 3. From figure B, the function v of t can be obtained as, from figure B, this is the figure V, v of t can be obtained as v of t is given as 100 volts. Okay, so v of t is obtained as 100 into u of t. So here also we are applying the Laplace transform on both sides. We get v of s is equal to 100 by s. But we know that I of s by v of s is equal to h of s, or I of s becomes h of s into v of s. Okay, h of s into v of s. From this expression, how to get I of t? I of t is nothing but inverse Laplace transform of I of s. So that it is inverse Laplace transform of I of s, that is inverse Laplace transform of h of s into v of s, or h of s value is s by s square plus 2s plus 5, and v of s value is 100 by s. So s and s gets cancelled, so that it will become inverse Laplace transform of 100 by s square plus 2s plus 5. Or we can write this as 100 by s plus 1 whole square plus 4. This is s square plus 1 square plus 2s. Okay, so s square plus 2s plus 1 plus 4. So we can write this s square plus 2s plus 5 like this also, s plus 1 whole square plus 4. So it is in the form of some constant into a by s plus 1 whole square plus a square. Okay, some constant into a by s plus 1 whole square plus a square, that is nothing but whose inverse transform is e power minus bt into sin at, e power minus bt into sin at. Here b value is 1, so that it will become mm, it will become e power minus bt, e power minus bt, that 50 is constant, e power minus 1 into t into sin 2t. Okay, 50 into e power minus t into sin 2t. So I of t value is 50 into e power minus t into sin 2t. So like this we can find out the I of t value for this problem. Okay. Okay, so this is about the problem, and this is next. This is some other type of the problem. Like this, we have two more problems are there. Okay, two or three more problems are there. So long problems. These are all. See this one. See, a signal f of t is equal to 2 pi by omega into delta of t minus SCA into omega t by 2 is applied at the input terminals of the ideal low pass filter. The transfer function of such filter is given by, here also a transfer function is given. Transfer function is given, and f of t is given. What is meant by transfer function? The output function by input function. Here the input function is given and transfer function is given. Only we have to find out the response, that is the output function. We have to find out the output function. So given input signal is f of t equal to 2 pi by omega delta of t minus SCA of omega t by 2, and Transfer function is given as h of j omega is equal to kg into w of omega into e power minus j omega t naught, where g into w of omega is a gate function. G into w of omega is gate function and the value 1 for limits minus 1 by 2 is less than or equal to omega is less than or equal to 1 by 2. Otherwise, its value is 0, which is called gate function. G into w of omega, g into w of omega, which is varying from minus 1 by 2 to plus 1 by 2 with some unit amplitude. Some unit amplitude. So that is called gate function. Okay. So let y of t is the response of the filter, then y of t equal to, so y of t is nothing but in input signal convolved with the impulse response, that is f of t convolved with h of t. From this, y of j omega is equal to f of j omega, into h of j omega. Since convolution in time domain becomes simple multiplication in frequency domain, so y of t equal to f of t convolved with h of t is nothing but the convolution in time domain, whereas y of j omega is equal to f of j omega into h of j omega is nothing but the simple multiplication in frequency domain. So now we'll take the Fourier transform of f of t. So f of j omega is nothing but the Fourier transform of f of t. So it is minus infinity to infinity 2 pi by omega into delta of t into e power minus j omega t dt minus integral minus infinity to infinity sa means that is sa into omega t by 2 into e power minus j omega t dt. So f of j omega is equal to delta of t. Delta of t is impulse function which exists at t equal to 0. So it is 2 pi by omega into its value is at t equal to 0. Its value is 1. Okay, delta t value is 1 minus integral minus infinity to infinity. This is by sa of omega t by 2 can be written as sin omega t by 2 by omega t by 2 into e power minus j omega t dt. We know that Fourier transform for a rectangular function of t by tau is equal to sin omega tau by 2 by omega tau by 2. Then by dual property we have Fourier transform of sin omega tau into t by 2 by tau t by tau is equal to 2 pi into rectangular of omega by tau. Here tau is equal to omega and rectangular x is equal to gate function, that is g of x is equal to, that is nothing but g of x. So therefore Fourier transform j omega is equal to 2 pi over omega minus 2 pi into g into w by w by omega by w into omega by w. So g of omega by w with limits minus omega by 2 to plus omega by 2. Now using equation number 1, we have y of j omega is equal to 2 pi by omega minus 2 pi into g for omega by w into kg into w of omega into e power minus j omega t naught. By using the inverse Fourier transform, y of t becomes 1 by 2 pi into integral minus infinity to infinity y of j omega into e power j omega t d omega, or it is equal to 1 by 2 pi into integral minus infinity to infinity y of j omega value is the above one. 2 pi by omega minus 2 pi into g into w by omega by w into kg into w of omega into e power minus j omega t naught. Okay, so by simply substituting these integral values, so that it will become solution of first term of equation number 2 is y of t is equal to 1 by 2 pi integral minus infinity infinity 2 pi k by omega into g into w of omega into e power minus j omega t naught into e power j omega t d omega. Apply the time shifting property here so that it will become y of t equal to 2 pi k by omega into g of t minus t naught, that is considered as equation number 3. Now the solution of second term of equation number 2 is y of t equal to integral minus infinity infinity kg into w of omega into g of w of omega into e power minus j omega t naught into e power plus j omega t d omega. Here we have three cases are there. So case 1, here we are considering omega equal to 1. Case 2, for case 2 omega is greater than 1, and for case 3 omega is less than 1. So for case 1, in this case the figure 2 becomes, our figure 2 becomes g of omega by w by omega, g of omega by w varying from minus 1 by 2 to 1 by 2. The limits of the above integral are minus 1 by 2 to plus 1 by 2. Y of t is equal to minus 1 by 2 to plus 1 by 2 k into 1 into 1 into e power minus j omega t naught into j omega t d omega is equal to k into integral minus 1 by 2 to 1 by 2 e power j omega into t minus t naught into t omega. Okay, so by simply substituting this one, so that it will become k into sin t minus t naught by 2 by t minus t naught by 2. Therefore, y of t is equal to k into sink of t minus t naught by 2. So y of t becomes k into sink of t minus t naught by 2. Okay, right. Then coming to the case 2. Case 2 and case 3 is also there. Here we are checking in three different cases. Okay, so case 2. So in this case, the limit value ranges from minus 1 by 2 to 1 by 2 as shown in figure. So, so here these two functions are multiplied. Multiplied g of omega by w, which is having the limits minus omega by 2 greater than minus 1 by 2 and omega by 2 is greater than 1 by 2, which is multiplied by g of w of omega, with the limits minus 1 by 2 to 1 by 2, which amplitude 1. So, so it will become g of omega by omega. So the next range is from minus 1 by 2 to 1 by 2. G of uh, omega by w is multiplied by g of w of omega. Okay, its limits minus 1 by 2 to 1 by 2. Okay, so by simply multiplying these two, we will get the value of y of t equal to k into sink of t minus t naught by 2. In the above case, y of t value is k into sink of t minus t naught by 2, right? And third case is this one. Third case is this one. For this case, the limit values ranges from minus omega by 2 to plus omega by 2 as shown like this. Yes, here also we are taking the multiplication of these 2g of omega, w of omega into g of omega by w. So by simplifying this one, we will get the expression for y of t is k omega into sink of omega into t minus t naught by 2, that is treated as equation number 6. Thus, y of t equal to 2 pi k by omega into g of t minus t naught minus k into sink of t minus t naught by 2 for omega is greater than or equal to 1 from equations 3 and 4. From equations 3 and 6, we can say that it is 2 pi k by omega g of t minus t naught minus k omega sin omega of t minus t naught by 2 for omega is greater than or equal to 1. Okay, so with this I will conclude today's session. In the next class we will do some more problems. Okay, thank you.